Okay. Right. What we're going to do now is get into thermodynamics. We're going to apply equilibrium here as well. But thermodynamics really looks at why why chemical reactions take place, what drives them, what makes them go, and also how much work can actually be done. Can you get out of a chemical reaction? Uh, and a lot of chemistry. What's really important is not just doing chemistry and making things. It's how much energy, free energy, that we're going to talk about here, that is released or absorbed in a chemical reaction that can actually be applied to do a work system and surroundings. We're going to be learning about a new term called entropy, which I had touched on slightly before. It's a very important concept, and generally, it is considered the main force that makes, well, I mean, not really force, but the main driving entity that makes chemical reactions go in the direction that they go. So we'll be touching on that. We'll be applying equilibrium to that. And also, I mean, equilibrium is just that when you have the rate of product and the rate of reactant are formation are equal, and there, but the amounts aren't equal. And why we have equilibrium is because systems are trying to balance out, in a sense, their entropy in terms of reactant and product. We'll be just touching on this for further discussion on thermodynamics. You really should take a physical chem class. That will really get in the key. It gives you the full background in it, and then go maybe take a statistical mechanics class. Uh, that that will help as well. Okay, but let's just move on here to our new topic. Okay, thermodynamics is a study energy changes in the flow of energy. Um, so one of the things we'll be looking at is it possible for a given reaction to occur? I mean, usually we just say chemical reactions occur, but they don't always happen. Um, but we talked about last semester that you had to have when we're looking at single replacement reactions, there had to be the right combination of metal and ion for the chemical reaction to take place. If you had the wrong combination, the reaction wouldn't take place. Well, why is that? Okay, so not all chemical reactions take place, and what we're going to be looking at now in this chapter, the next chapter we'll see how it applies to single replacement reactions. But is what makes a reaction take place? What makes it drive forward? Now I told you that all reactions technically could be take place both directions if they are if you have an isolated system. Most of the time we don't have an isolated system. We're losing energy, we're losing matter, and as we lose energy and matter, those two things can't re-enter the equation to move back towards a reactant. But they are. All chemical reactions can move backwards and forward, and will have an equilibrium expression. Now, if a reaction looks like it goes completely to right, even in an isolated system, that means the KSP is very, very, very large. Okay. And so, or not KSP, just the equilibrium constant, is very, very large, and there's essentially almost no reactant left over. But there probably is a little bit. But anyways, so some other things. So also, going with the first thing here, given a reaction to occur, if a reaction occurs, what we say, does it occur spontaneously? That means once you get over the activation energy, which we talked about And 121, after you go over that hump, will that reaction keep on moving forward towards the product without any more help? Okay, and we'll discuss those. Also, which we talked about last semester, some reactions give and absorb heat. Reactions that release heat are called exothermic, and reactions that absorb heat are endothermic. Again, like enthalpy, we are just looking at the state of a system, and the new terms that we be talking about, entropy and free energy, just are what the systems are as they are. We don't know how they got there. All we know is that there's a beginning and end, and all we do is we can measure what they are at the beginning and what they are at the end, and we're not going to consider how they get there. If we did that, we'd have to talk about kinetics, which we did when we talked about rates of reactions. Okay, two of the main things that are going to help us answer these questions are going to be changes in enthalpy, which we talked about, and 121, and this new term, entropy, which is kind of described as nature's trend towards randomness or disorder. Entropy is got 2 or 3 kinds of definitions. It can have definitions in terms of its macro properties, like talk about messiness or whatever. But we're going to talk about in terms what way of thinking about it conceptually, and hopefully won't destroy it by doing that. Okay, so let's go back in 121, and we talked about enthalpy. Enthalpy, remember, was the the internal energy of a system at constant pressure. And we can measure, and when a chemical reaction takes place, the enthalpy of the reactant will be different than enthalpy of the product. So there's a change in enthalpy. And the way that we can measure that change is by measuring the heat that is absorbed or released in the chemical reaction. If there is a release, if the reactant loses internal energy, as that internal energy will be released as heat and will heat the surroundings, and that's an exothermic reaction. An endothermic reaction is the opposite, where heat is absorbed into the reactant and increases its internal energy. Okay, now we'll come back to enthalpy in a few minutes, but let's talk about spontaneity. Now, spontaneous is a chemical word. You've probably heard it before, but we're going to use it as a chemical term. The spontaneous change is one that occurs by itself. What that means is that you have to first give it a boost, give it the energy of activation, but once you get it going, the reaction will keep on taking place. Like a fire. Okay, all you have to do is take a match to a tree, and that match causes the chemical reaction of combustion to go over to energy activation. Then it just takes off, and the fire can keep on expanding as long as there's fuel. It doesn't need any other help. You don't have to keep on adding a match. And here's a couple of things, like water going downhill is obviously spontaneous. Or melting ice on a warm day is spontaneous. It just happens. You don't really need to do much. If the temperature is a constant, and we're talking about temperature constants when we do these, because we're talking about states of systems. And okay. Okay, non-spontaneous changes require help. Okay, you can light a match, but it'll keep on going out. Here's some examples. Like, a room doesn't get straightened up all by itself. Okay, that's not spontaneous. Bricks don't turn into a wall. Okay, water can't split into oxygen and hydrogen just by sitting around. What you have to do for each one of these, you have to have a person clean up the room. That's outside help. You need a bricklayer, okay, outside help. And you need electrical current, which is outside help. But once you remove any of these things stop happening. Another example of this is photosynthesis. Photosynthesis, once the sun goes away, goes the night, photosynthesis technically stops. But once the sun comes back, it starts back up. Okay, I don't want to talk a lot about this, but I hope you get the general idea. Okay, now, so what we want to do first is look at is how does spontaneous reactions relate to enthalpy. Then we'll expand that to further terms. Okay, so exothermic reactions almost are all spontaneous. Iron rusting. Okay, you don't need to have. Rust just happens. Okay, trees just burn down. All of these are exothermic reactions. They give off heat. Okay, in the process, heat is given off. Energy is leaving the system. Okay, now, why would exothermic reactions tend to be spontaneous? Okay. Okay, so let's consider you have a book, and you raise the book up and above the ground. All right, and then you let go of the book. The book is not going to stay up in the air. It's not going to be like Harry Potter. It's not going to stay up there. It's going to fall to the ground. Okay, nature has a tendency of things going in a direction. And usually the way that it goes is things will try to lower their potential energy to get in a better state. Okay, now the reason why that happens is, if you think about the book, what did I need to do to get the book up in air? Okay, well, I need to lift it up. Where did I get that energy? So I had to apply energy. Well, I had to get the energy from somewhere else. I had to get it from my food, maybe my hamburger. Well, how did I have to get my hamburger? I had to go kill a cow. All right. Well, I had to. Where did the cow come from? Well, the cow had to come from growing a bunch of wheat in a field and having it eat it. Okay. Well, where did I get the wheat? Well, I had to grow the wheat from seeds in the sun. And so if you look at just to do the simplest thing, it actually requires a whole lineage of energy to get it there. And that's just not natural. You got to keep on going back, grab a hold of energy. So naturally things don't want to use energy because you always have to go back and get the energy, right? And so they'd rather stay as they are. And this kind of relates to the idea of inertia. Things stay at rest unless something's applied to them. So, in a sense, when a exothermic reaction takes place, you have a system that's sort of stressed. It's got a lot of potential internal energy in it. And it's not where it wants to be. It's kind of been lifted up in the air. And then when the chemical reaction takes place, it loses that energy and falls to the ground, and then you have the product. So the product, in a sense, is more stable than the reactant, and it gave off energy. So anytime a system looks like it wants to go, in terms of thermochemistry, goes from something that has lots of internal energy to less internal energy, that's what is favored. So exothermic reactions tend to be always favored over endothermic reactions because they give off heat, they give off stress, they give off energy. So a chemical reaction that's exothermic is usually, well, for all we know, they are spontaneous because that's the way nature goes. Nature wants to release energy. Okay. All right. Okay. Now, from that discussion, it implies that endothermic reactions that require energy to happen, lifting the book up in the air, should not be spontaneous. I mean, a book doesn't just lift itself up in the air, okay? But it turns out that there are some endothermic reactions that happen spontaneously. It kind of goes against our natural intuition about things, okay? So it's like all of a sudden the book lifts itself up in the air, okay? Examples of that are like ice melting above room temperature, okay, above freezing. Ice is an endothermic reaction. How do you know it's endothermic? Because you can feel it taking heat from your hand. So when you grab a hold of ice, instead of warming things up, it cools the surroundings down. The heat from your hand goes in the ice cube, so it's absorbing heat from your hand, and it's making water. So actually the water has a higher enthalpy than the ice. Okay, so and there's several types of endothermic reactions that are spontaneous, but overall you don't see many of them, but you do, and then that's what's curious here. So delta H is positive, heat is absorbed, energy heats, but nature does not prefer adding heat to make things work. Okay? Why? Because the energy has to be found and given, just like we talked about lifting a book up. Okay, so it's like lifting a book up in the air or pushing a car up the hill. Okay, the hill rather come down. I mean, the car rather come down the hill. So overall, endothermic reactions are inherently not preferred because they require energy to work, to get going. But they do. They can be spontaneous. And once you get them going, they'll keep going. But usually, spontaneous reactions are exothermic. But there are some endothermic reactions that are spontaneous. And also, there are some exothermic reactions that are non-spontaneous, which is counterintuitive. And we're going to look into that. So, big thing is this. Why can some endothermic reactions take place? And as long as saying, well, similarities, is why can some exothermic reactions not take place? So what we're looking at is what I mean by take place is be spontaneous. So enthalpy is not the only thing that affects if a reaction takes place spontaneously. And so what we want to do is introduce a new term that will help us decide if a chemical reaction takes place. Okay, and the new quantity we're going to help explain why some chemical endothermic reactions can be spontaneous and why some exos can't be spontaneous is introducing this new term called entropy. And we're going to give it the symbol S. It's a thermodynamic quantity. That means we can measure it. Okay, we can measure its value. We can measure if we have a state, we have a system. We can, just like we measure temperature, energy, enthalpy, pressure, volume, how many particles in a system, we can also measure entropy. Okay, entropy has at least 2 or 3 different ways that it can be defined. One of the ways is it describes how many ways a system can be split up. Right. It kind of tells us, because of that, if a system can be split up in many ways, that means it has a large probability of different things happening. And so it would have more randomness. So it can be described as a statistical property. So as a state becomes more and more larger and distributed, it gains more entropy. So larger S means more possible ways to distribute energy and particles. And you can get more and more possible and probable results. Okay, so this is just a little diagram. What happens is that if molecules can spread out over a little bit of energy, this has less entropy. And if it can spread over a whole lot of different energies, this is higher energy. So it has more states it can be in. So if particles can be in more states, that means it has a higher entropy. Okay, and what nature prefers is nature prefers more and more states, given states. Okay, it prefers to spread out. Okay, if you're given if nature was given a choice between having the reds, so the yellows here, okay, what would happen is these guys would, if the redwoods were given this amount of space spread out versus to this space, they would spread out in this space more better, this space. That's, think about, like when you put a drop of food coloring in the water, it spreads out, okay? And it finds more and more probable, possible configurations to be in. It increases its entropy. And notice it does it naturally. Nature is always going to, the tendency in entropy is nature moves towards increasing entropy, increasing possible states. Okay, so here's an example. Suppose you had a $2 bill. $2 bill is basically a low entropy system. There's only one state. But you could have two $1 bills, so this would have higher entropy. And then you could do all these quarters. These quarters are still $2, but they have more states. Therefore, it has more entropies. So a system having more possible states within a system of entropy, states of then it has higher entropy. And you probably know that if it's easier to, I mean, if you have eight quarters and $1 onto a $2 bill, these can spread out all over the place. Okay. All right. Okay. Back to spontaneity. And here's some things that we just talked about. All right. Okay. Now, so let's look at each one of these. So things get rusty. Okay. This is a exothermic reaction. And so, but one of the things to notice about is you have it go from shiny to rusty. So shiny is kind of like a more ordered situation, and rusty is a less ordered. Okay, it flakes off, rust flakes off, and shiny took a lot of energy sort of to make it the way it was. So one of the things we're going to kind of relate this spontaneous to is order and disorder. Things that are more ordered have less entropy, and things that have less order or more disorder have more entropy, and we're always going towards more entropy. So is this reaction, not only is it exothermic, it actually increases its entropy. So we got two things going on. We have enthalpy and entropy. Okay, so when you take sugar and dissolve in water, what you're doing is you're taking a very ordered thing, a sugar, and when you put it into coffee, it dissolves. Okay, it spreads out. It goes from a very ordered piece to a disordered. Right, ice. Ice goes from very ordered to disordered. Okay, at room temperature. And then fire, which is exothermic. So ice, so ice going to liquid, that's an endothermic reaction, and has an increase in entropy. Okay. All right. Fire burns wood, and smoke is going up into the chimney. So fire is wood is very ordered, smoke is very disordered. So you have a reaction that's exothermic and an increase in endothermic as well. And so what we're going to see is, as we look at chemical reactions, we're going to see two things happen. We'll be looking at exothermic and endothermic. Now, one of the common things behind all these guys is not if they're endothermic or exothermic, is that they all increase their entropy. Okay. So we're going to use those two terms. So what we see is what makes ice melt is not what lifts it up. What gives it more, even though it's endothermic, why does it take place is because it increases entropy. So what we're going to do is look at those two factors, entropy and enthalpy. Okay, at this point you might want to take a little break. So this is about 30 minutes. I'm not going to split this up into zones, but so what I'm going to do now is we're going to get more specific, talk about quantitative relationships of entropy, how we can measure it. And actually, how does it affect? Right now, we just talked about its concepts, okay? Increasing the disorder. Okay. So, entropy. Okay. So what we want to do is measure the entropy before and after in a chemical reaction. And what we would like to hope is that usually a chemical reaction will take place if it has an increase in entropy. Okay. And so what we'd like to do is measure so the change in entropy, just like any kind of change we talk about, is always final minus initial. Okay. Or product minus reactant. All right, so we're going to look at some of the things that affect the entropy. One is volume. If you have a gas in a small volume and increases volume, it'll be able to have partition off into more possible states, and therefore it increases the entropy. So if you increase the volume, you can increase its entropy. Another way you can increase entropy is into increased temperature. If you increase temperature, you get particles vibrating. That gives them more possibility of spreading out and finding new configurations. Okay, the state of a system has an effect on its entropy. Solids are more ordered, and they have more crystal structure, and so they're going to have low entropy. And then gases have increased entropy with liquids in between. And the reason why this is the gas particles have more possible states to explore, so they have higher entropy. If you have two systems where you have a certain number of particles, particularly gases, where they can move around more, a system with more particles is going to have more entropy than a system with less. So we have volume, increase in volume increases entropy, increase of temperature increases entropy, change of state from solid towards gas increases entropy, and also increase the number of particles will tend to increase entropy. Okay, which represents an increase in entropy? Water vapor condensing to liquid. Okay, so this is going from a gas to a liquid, so this is actually going to decrease the entropy because you're going from a gas to a liquid. Okay, carbon dioxide subliming. Okay, subliming is going from solid to a gas, so this is definitely going to be increasing entropy. Liquefying helium gas, that's going to be decreasing entropy. Proteins forming amino acids, that's going to be decreasing entropy as well, because you're taking a bunch of things, amino acids, and forming one thing, a protein. So the only one that actually you're increasing entropy, this should be dry ice sublimation. Okay, so all right, if you take a look at a chemical reaction, or I don't have one written here, but let's say you took methane, okay, so another thing to take a look at is the number of particles or moles a chemical reaction starts out with and how many ends up with. So let's say you have combustion of propane, and that's going to be in balanced equation. It'll be 1 propane plus 5 oxygens yields 3 carbon dioxide and 4 waters. Okay. There's an increase of particles. There are 6 particles on the reactant side and 7 particles on the product side. So 1 propane plus 5 oxygen is 6. 3 carbon dioxide plus 4 waters is 7. So if you see an increase in particles in the chemical equation, doesn't mean it's going to be that the reaction is going to increase its entropy, but that can help increase the possibility of the entropy of the system. And that's what this means. Now, the other thing is that if you have the numbers, if it actually goes along the same lines, if you have more gas particles, you'll have more tendency for disorder. Okay, so these are kind of things when you look at a chemical equation. If you see the number of particles increase, number of products, reactants is less than the number of products, then there is a tendency for increase in entropy. Okay. Right, here's an example where you have nitrogen plus hydrogen gives me ammonia, and then count down particles, there's 1 plus 3 is 4, and there's 2 over here, 4 is greater than 2, so this actually looks like it's decreasing its entropy. And so this might actually make the reaction, entropy decrease. It's a way of at least predicting if the entropy increases or decreases. Okay, same things with these. So formation of gases always tend to drive a reaction towards entropy. So notice you have the states here. You have a solid, aqueous. So what you have here is you got a change of state where you have solids, liquids going to gas. That means this reaction looks like it's getting more entropy because there's formation of gas. It's not really, this really isn't the key thing. The key thing here is you get a change from solid, liquid, aqueous to a gas. So this system is getting more entropic. All right, this reaction, since we all have gases, what we can do is count the number of particles. So you have 2 particles over here and 5 over here. So the reaction is getting more entropic. Okay, this should be liquid water. So you have 3 liquids in a sense. So you have 2 going to 1. So the entropy is getting is actually going down, decreasing its entropy. So if you see things change state, look at the state changes. Okay, if everything is the same state, then just compare the particles. Okay, so let's look at these. So you have a solid going to a gas. That means we expect the change in entropy to be positive. Okay, so, and this is dry gas. This is dry ice sublimating. So this is condensing. So gas going to a liquid, that'd be negative. Right. So here is, we don't know the state, so we just assume that all states are the same. So all you do is look at the number of particles. You go from 1 particle to 2 particles, so that increases the entropy. Okay, and in this case, you're actually having 2 effects, okay? The first effect is you look at the number of particles. The number of particles goes from 5 to 2, So that looks like it's decreasing the entropy. And also, well, you're also decreasing the entropy because you're going from a solid liquid to a solid. Okay, so this should be negative. This relates to this one. Sorry. So this one is negative for two reasons. It goes from 5 to 2, and also goes from solid liquid just to solid. This one, food coloring going to glass dispersion. That's entropy increases. Okay, your turn. Which of the following has the most entropy at standard conditions? Standard conditions: 25 degrees C, 1 atmosphere, or 298 K. All right. Okay, which one has the most entropy? Well, okay. Probably going to be B. Here, let's explain why. Okay. Okay. This has the least amount of entropy because it's a solid. And then we have our choice between these. Okay. Aqueous solution has things dissolved in the water. And therefore those things are moving around, so there's more particles floating around in the water. And just water. Okay. So the aqueous solution is going to have more disorder because of the particles that are dissolved in it. Okay, which reaction would have a negative entropy? That means get more ordered. Okay, so let's look at the first one. Okay, you got 2 particles going to 1 particle, so that's definitely decrease in entropy. And you're also going from aqueous to solid. That's also negative. So we have 2 things that really make this one negative. So right now, it's looking like this one is definitely a negative entropy. Now let's look at the other ones. Okay, B, you have both of them are gases, so you just look at the number of particles. Say 1 particle going to 2, so you're increasing the entropy. So this is not negative. C, you have 1 particle. We'll look at the number of particles. Goes all right. Actually, look at state, because the states go from liquid gas to gas. Okay. So this definitely is, you have a state change going from liquid to gas. And actually get increased number of gas particles from 25 halves to 17. So this is definitely increasing the entropy. And this one is also increasing the entropy because you go from a solid to 2. You go from 1 thing to 2 things, and also you're going from solid to a gas. So these are all ways to predict the entropy. They won't tell us exactly what the entropy is, but they're giving us an idea which reactions we think will be positive or negative entropy. Now, nature prefers increasing entropy. That means positive. That means A, if nothing else is affecting it. Okay. If we discount enthalpy, this reaction is the least likely to take place. Okay. Often entropy is related to messy. Nature prefers messes over neatness. Why? Okay, I just explained it. Okay, it requires work to clean messes. Where do you get the energy to do this? Well, if you're if you're living with your folks and you have a messy house, your messy room, your parents come in and say, clean your room, or you tell your kids to clean their room, they're not really want to do it. Why? Because it's going to require work. And why is that hard? Well, it's because you have to move. Okay, and remember, matter has inertia. All right, and so to do something requires work, and to clean messes needs work. Now, messes can just naturally happen. You don't even need to work at them. They just happen. It's like heat moving from hot to cold, right? Order always moves towards disorder. Okay, now what we're going to do is we're going to apply those two factors together. Entropy and enthalpy. And both of them are going to have an effect on if a reaction is spontaneous or not. And so what we have to do is take a look at both of them. Now, what we said earlier is that enthalpy decreasing is preferred. Things rather lose energy when they take place, give off heat. In terms of entropy, entropy is preferred to increase, and that's because things like to get messy or spread out. And so every chemical reaction will have both those components, and we have to look at both those components to see if maybe they're both preferred, maybe are both neither of them preferred, maybe there's a mix. Now we're going to look at that. Excuse my spelling here. That's increasing. It's increasing. Okay. So which one prevails? Okay. So what we got to do is we're going to take all three of them and help them define how a chemical reaction takes place. Okay. So we know that ice melts above 25, which is spontaneous. But if you go below 25 degrees, if it's at below 0 degrees Celsius, it freezes. So it's spontaneous below 0. And it's spontaneous melting above 0. Okay? And at 0, it turns out that they actually do both. They're in equilibrium, thermal equilibrium. Okay, now a more formal definition of entropy is included what we call the second law of thermodynamics. The first law of thermodynamics basically says that the energy you put into something is equal to the amount of work and heat that comes out. Okay, and there's no loss of energy. So some of the energy that goes in the system can do work, the rest will do heat, and we should be able to count all those up, and they should equal the work going in or out, plus the heat going in or out should equal to the energy that was originally given to the system. The second law of thermodynamics includes entropy, and that says that the total entropy of the universe is increasing. It's not kind of increasing, it is increasing. It is always increasing. It turns out it's like the only thing that we're sure of is entropy, is that it's always increasing. A spontaneous process, the delta S of the system can decrease as long as the universe's entropy increases. So some of the chemical reactions we're going to see is that there's going to be the entropy is actually going to decrease. And by the way that nature is, that it's like having your room just automatically clean itself up. Okay, well, that can't happen unless the rest of the universe gets more disordered. Okay, so what must have happened is some energy from outside must have come in out of your room and cleaned it up. Okay. So if a system actually decreases entropy, that means the rest of the universe's entropy has increased. Okay. I mean, that's sort of what happens when you make ice cubes. All right. An ice cube is what you're doing is that you're freezing it. Okay. So you got to cool down the air. Well, when you cool down the air, what it does is it warms up the rest of the air more than the outside air, then it's cooled down the air inside your refrigerator. And that's one of the hardest things about cooling and any kind of cooling system. If you have a cooling system, it's got to draw heat from the outside. Okay, and what it's got to do, if it cools the inside, the outside gets warm, and it doesn't just get warm. As warm, the cool down inside doesn't. The warm on the outside doesn't equal to the coolness on the inside. The outside actually gets more warm than it cools down on the inside. There's an increase in the entropy on the outside. Okay, it's not equal. All right. So when you cool something down, you're not just taking heat away from it. You're taking the heat away plus. Okay. So if you decrease the entropy, you're increasing the rest of the universe's energy more than the amount you have actually decreased the energy of the entropy. Okay, now that's a little bit hard thing to kind of understand because this is not an equal thing. Entropy is not conserved. It's always increasing. Okay, formally we can write out that the total change of energy of the universe is equal to this entropy of the system plus the entropy of the surroundings, and this has got to be an increase over here. Okay, so overall both of these have to add up to a positive value. So the S of the surroundings is going to equal to the heat of the surroundings divided by its temperature. And this is actually a formal thermodynamic definition of entropy, which we are sort of skipping over now. But that's what's still going to use this formula. Okay. The Q surroundings is equal to minus Q of the system, and so forth, and we can write it out. The change in S of the surroundings is equal to the minus H, the change in enthalpy of the system over T. And we're not gonna get into this. I'd like to get more informal with it. But let's just start using it in an equation and see how it applies. And if we had more time, we'd study a more theoretical and conceptual basis behind this relationship. Okay, and so what we can do is we can plug this into the original equation, substituting surroundings with this term, and then just multiply both sides by t. Keep them over here, and then we get this equation here. Okay, now this number here has to increase. Okay, we said that entropy. This is the entropy of the universe. It has to equal 0. That means that when you put the inequality in here, you get this relationship. Okay, which says that this term here must be negative for the reaction to take place. So what we do when we look at a chemical reaction, we measure this term, the enthalpy of the system, and the delta S of the system at a given temperature, And if that number, if the combination of those two numbers, and we'll see how this applies in a minute, is less than 0, then the reaction is spontaneous. Okay. So we just don't want to have that inequality as inequality. We actually want to give it a value. And so what we're going to do is we're going to set that term, the H of the system times T S system, equal to G, which is called Gibbs free energy, which is the maximum amount of energy that is free available to do work. And here's our equation. So this is a pretty big deal equation, and we'll be using it as we go on here. So what we want to do for a spontaneous reaction, delta G should be negative, and for a non-spontaneous reaction, delta G will be positive. Okay, as we state here. And when delta G is equal to 0, we're at equilibrium. Right, when we put these terms in, delta H is joules per mole, temperatures Kelvin. S is going to be in terms of joules per Kelvin. So joules per Kelvin times Kelvin, it just leaves me with joules. So I'm going to have joules minus joules, and so Gibbs free energy is in terms of units of energy. Okay, so let's look at our formula and see how it relates to our equation. Okay, so you have delta G equals H minus TS. Okay. All right. Now, so let's say that we're going to take these two conditions here. We're going to take when the enthalpy is negative, which means it releases energy. That's good, remember. Okay, the enthalpy is going down. And we're going to look at delta S. There's an increase of entropy. Notice both of those are preferred. Okay, that means this reaction will always take place. Now, if we plug it into the equation, we'll have delta H will be a minus term. Delta S will be a plus term, so you have a minus times a plus. And so you have minus plus a minus will give me a minus. Okay, so not only does conceptually it make sense that that this reaction won't take place, but using a formula will, because this will always be a negative term. Okay, now let's look at the opposite. So let's say you have an increase in entropy, add energy. All right, and you ought to also decrease the entropy. Both of those are bad. That reaction is not going to happen. And if you plug terms in, you have a plus term. Then minus times minus is also plus, so you have plus times plus, which gives me a plus term. So the equation and the conceptual make sense. All right, now let's look at a mix. Now let's say the delta H, there's an increase in the enthalpy. Okay, so that would be like melting water. Okay, so when you have ice. When you have ice, what you do is heat is moving from your hand to the ice, so it's an endothermic reaction. That's not favored. Nature does not prefer endothermic reaction. You're lifting it up. However, you're going from a solid to a liquid. Okay, so that reaction looks like it can be both. It has bad in terms of enthalpy, good in terms of entropy. So when do they happen? Okay, well, it is temperature dependent. Okay, and that means if you increase the temperature, if you have a high temperature, that'll make this term more negative, and so the reaction will take place. And you can see that if you raise the temperature of ice, okay, it melts. Okay, so if both of them are good, both of them are positive, these reactions will take place at higher temperatures. It's temperature dependent. All right, now if we look at the other situations where you have a good and a bad, where you have, in this case, it's actually the opposite. This is where you freeze ice. Okay, if you freeze ice, what you're doing is, actually, it's hard to, when you freeze ice, what's happening is heat is being removed from the water, and so it's, in a sense, it's giving off heat. So this reaction, so when you make ice, it is a exothermic reaction. Heat is leaving, okay? We know that's good. But that it's bad in terms of entropy because it's going from a solid to a liquid, okay? So one is good and one is bad. Okay, so this reaction can actually be either depending on the temperature. If the temperature, in this case, if the temperature is low, then this reaction will take place because you'll have a low, that will make this number really low and just have a greater effect. So when they're both negative, lower temperatures are better at producing a spontaneous reaction. Now it turns out that you can have a point where these guys equal each other out, where they balance the good balances out with the bad, and that will happen at a specific temperature. That's like at melting at 0 degrees. At 0 degrees, we are at thermal equilibrium where the good and the bad are equal and the reaction moves back and forth. These first two up here do not have thermal equilibrium because they will either always happen or always not happen. Chemical reactions that have a combination of good, bad, all right, they can have thermal equilibrium. And we'll get to that in a little bit. Okay, go ahead and try this one. Plug her in and see what you get. Okay, so this is sort of the second half of that was the second part of this lecture. So if you want to take a break here, that'd probably be good because I know it's tiring listening to my voice. I'm tired of listening to it too. I wish I could be more exciting and have pictures to draw and movies to show you, but do what you do when you got Corona in our world. All right, so okay, so I will probably be able to finish it up in this half hour, but maybe a little bit more, but we'll see. So what we're going to do is now introduce the third law of thermodynamics. And the third law says is that we have something called absolute zero temperature. And at absolute zero, the entropy is zero. Or the entropy is zero. That means it's completely ordered. Okay. All right. So there is something... everything technically, theoretically, can have an entropy of zero if you bring it down to 0 And what we do is to figure out the entropy at a certain temperature, what we do is we increase the temperature and then measure its change in entropy going from 0 to 298. Now, this is very difficult, and there's ways of doing it. There's no such thing as an entropy meter. It requires other means of doing. And again, if you want to get more into this, you would take physical chemistry. All right, consequences of the third law. All substances have positive entropies. All right, that's because they're all above 0K. And why is that? Because heating increases entropy. S is greater than for gases, more disordered. Basically, this is what we're saying is that all substances have entropy, and it's all greater than 0. And the units of entropy are going to be joules per mole per times Kelvin. Okay. What we can do is we can measure if given a chemical reaction, we can measure the delta S of the reaction of the change in entropy from reactant to product by using a similar reaction formula that we used when we found delta H using the S of formations. What you'll notice in your book, or if you just look on tables, is that whenever you look up a table of heats of formations, you also often find S of formations and delta G's of formations. And so what we can do, given a chemical reaction and a set of S's for our substances, we can figure out the delta S. And here's an example. Again, it's going to be delta S to be the product, delta S minus the reactants delta S. So you look up on the table, the delta S, and sometimes they just give you S, not S. So actually this is just the S, not delta S. So they give you the S of the substance and the S of the substance. And then then what you do is you take product, subtract reactant, and then you end up your value. And I should have put a plus here. So the delta S is plus 26.1 joules per Kelvin a mole. So there is an increase in entropy. Now, if you look at predictability of that, we would also say that we predict that it would increase the entropy as well, because it goes from a solid to gas. So our actual prediction, is verified by our actual numerical results. Okay, so here's another chemical reaction in this one. So you find the S for each one at standard conditions, and write them down. And then what you do is you add the two products together, these two terms, and then you subtract the entropy and the entropy. Now these will always be positive values. All right. So you add these two, subtract this one, and then you get positive ones. So there's an increase in entropy, and that's kind of what you expect here, because you go from one particle to two, and you also go to a gas. All right, so here's another example. So I have this equation here. Okay, and so what I do is I look up the values, and so it's going to be product, subtract, reactant. But remember, you have to multiply it by 2 and 3, so you're going to 2 times 28.3, 3 times 188.7, put those here. Then subtract the 51.0 times 1, and then 3 times 130.6, and do the math. Okay, so the moles cancel out, end up with moles cancel out, bubbles cancel out, moles cancel out, and wires temperature. Oh, you're left with joules per Kelvin, which is term for entropy. So, and again, you get an increase in the entropy. So this is a way of calculating the entropy. You can predict it by looking at the chemical reaction, but you can also but really what's more important is you can figure out numerically using this relationship, just like we did for delta H's in 121. All right, so here's another one, and you give it a go, and you can see that in this case, actually, there's a decrease in entropy. All right, so in this case, entropy is not favored, but we don't know if it will react or happen or not, because we have to look at the enthalpy as well. If the enthalpy is favored, that means if it's an exothermic reaction, and we have, so that means we have bad S and good H. That means there is a temperature where the reaction will take place, so it'll be temperature dependent. If it turns out that delta H is bad, endothermic, then this reaction will not happen. Okay, so we saw that we had a formula for delta G, where delta G is equal to delta H minus T delta S. And you just have to look those values up again in your tables. And then, or another way to do it is in the table, they give you delta G just like they do delta H and delta H and S. And you can figure out the delta G not only using this equation, but this equation as well. And both of these take place, we say, are 25 degrees C, 1 atmosphere. Okay, and here we go. Again, so what we're going to do is figure out the delta G using the H minus T delta S formula first, and then we'll be using the delta G the other way. Okay, so you look up the delta H, and we're gonna first of all find out delta H, and then delta S, and then do the math, and then figure out delta G. So we look up the delta H's in our table, and then we go 2 times 0, 3 times minus 241.8, add those together, and then subtract the sum of these two. Okay. And when we go through all of that, we get the change in enthalpy is 944.4 kilojoules. Now, if you notice this endothermic reaction, so far this reaction is kind of not favored. So let's just remember that, okay? It doesn't mean it's not going to happen. It just means and so far it's not favored in terms of enthalpy, okay? Now, this reaction will happen if delta S is positive and at the correct temperature. If delta S is decreasing, then this reaction won't take place. But it doesn't matter. We're going to see how that works out in a second. Okay, next thing is figure out the delta S. Okay, and we figured that out already. If you go back and look at example number 3, we already got that number. We saw that there was an increase in delta S. So what we have is delta H is bad in a sense. Delta S is good. So this reaction will take place at the right temperature. So this is temperature dependent. So let's see if it takes place at 298. So we plug the values in. So 290, H is 944. Temperature 298. And we want to get in terms of kilojoules. So that's why we're doing this over here. And then we do that, we end up that the delta G is positive 898.8 kilojoules. So this reaction will not take place at 298. Okay, but what we could do is determine what temperature it does take place. If we set this equal to 0, if we set temperature to 0 and then solve for, if we set delta G to 0 and then solve for T, we can find what temperature the reaction takes place. And since both of them are positive, both the delta H and delta S are positive, an increase in temperature, a temperature above whatever temperature you find, the reaction would take place. So so that's the kind of thing I would do here. I would solve for that, and we'll have an example of that in a minute. All right. Okay. So now what we're going to do is figure out the delta G using the values that were given in the table. All right. Okay. So now all you need is delta T. You don't need G, not S and H. Just look the values up, plug them in, and notice is that you get very, very similar answers. Okay. So either way, you can get the same answer just using different methods. Okay, it's delta H, delta G is important because when we actually look at chemical reactions, we look for the delta G and we determine if the delta G of the reaction can give us energy to do work. And here's some example. So when these people design batteries and cell phones and whatever, okay, they take into account delta G. And if you get into biochemistry, you'll be spending a lot of time with delta G as well. All right, now what we're going to do is apply this to equilibrium and see how it relates to what we already talked about, thermal equilibrium. Okay, so actually may want to just take a break here and then come back to it, and we'll be finishing it up here. All right. Okay. All right. So as I said, all reactions can be reversed, and really what we want to do is that when you have a reversible reaction, you like to just change it. We want to call it reversible. Okay. All chemical reaction reversible, because if you do it at a very, very small amounts, for instance, if you have a piston here, okay, with water sitting on top. Now, some of the time, so what's going to happen is it's just going to expand and contract, but it's always going to stay at this level of water and gas. That's because you may have one water molecule evaporating and then one condensing. And so there is a chemical changing take place. There is the reaction going this way and the reaction going this way, but it's looking like it's never changing. Okay, so delta G is the maximum possible work that can be done under reversible conditions. Energy that need not be lost to surrounding heat. So in this case is that what delta G is actually looking at is how much of the energy is going to be useful to do stuff. I mean, a lot of times when you do a chemical reaction, it gives off heat and it goes into the surroundings. In this case, what delta G does is it actually looks at the heat and entropy as how much can help to do work. Okay, so here's delta G reaction calculation. So just plug everything in as a given, and we find out that delta G is negative 358.5 kilojoules per mole. And this term over here is just to get joules into kilojoules. All right, go ahead and give that a try, and you got the answer there. Okay, so now let's see how this relates to equilibrium. All right, so when delta G is positive, that means the reaction tends not to have it happen. That means the reaction looks like it's sitting over in the reactants and not working, okay? But remember, all chemical reactions at equilibrium do take place. So when delta G is positive, what you have mostly is you have mostly reactant. It appears though it's not, as though it's non-spontaneous, is that the reaction is not taking place. But there is some of the reactant is turning into product. Okay. Now in the other case, when delta G is negative, that means the reaction is taking place spontaneous. You have, looks like you have product forming. Okay, so that means the equilibrium is being with more product on the right side. I mean, there's more product than reactant. So let's take a look in terms of equilibrium. In this first case, you have more reactant than product. So remember, equilibrium is equal to product over reactant. Okay, for when delta G is positive, that means there's more reactant than product. That means there'll be more of the denominator than the numerator. So that means K is going to be a decimal, zero, a fraction. Okay. All right. Now, when delta G is negative, you have more product than you do reactant. That means the equilibrium expression is going to be a number greater than 1 because there'll be more numerator than reactant. And so what we're going to do is take that relationship between equilibrium and free energy and put them together. Okay, when delta G is equal to 0, okay, that means you're getting both reactions taking place at the same time. It looks like the reaction is taking place either making or breaking. For instance, when water is at 0 degrees Celsius, there is both ice being formed and water being formed. All right, so when the ice is formed, what happens is that that's an exothermic reaction that releases heat, which melts the ice and makes more water. Okay, the water, it's more entropic, it's going to push reaction back and forth. So at thermal equilibrium, where delta G is equal to 0, the entropy and the enthalpy are balance each other out. Okay, so here's our relationship. So what we can do is we know that K, so if you have, K is product over reactant, so if you have a big K, you have a lot of product, the reaction will take place. And so what you can do is what we can do is relate, at equilibrium, delta G is equal to the gas constant temperature times the log of the equilibrium expression, and then we could rearrange it to solve for the equilibrium expression as well. All right, so here's what I just talked about. So if you have a K greater than 1, okay, that means there's more product than reactant. Obviously, that means the reaction has been spontaneous and made more product, and delta G is negative. Okay, if you're between 0 and 1, a fraction, that means there's more reactant to product. It's non-spontaneous, it's unfavorable, and its energy needs to take place. And when equilibrium is equal to 1, delta G is 0, and we're at equilibrium where entropy and enthalpy are balanced. All right, and here's just checking it on you again. Go ahead and see if it works. All right. Okay. Next thing is, let's say we have a system that's not at equilibrium. Okay, so what we want to do is see which ways it goes. So we can use our reaction quotient to help us figure things out. All right, here we have an equation. Okay, so we're just going to plug everything. So we have our Q's, so we put in we have our equilibrium expression. Okay, so it's going to be NH3, so it's going to be squared. Just P means pressure. So, and then we're all dealing with pressure here. So the pressure of the NH3 squared, because there's 2, divided by N2, only 1, and then H2, 3 of them. Do the math, and you get a reaction quotient of 9.3 times 10 to the minus 3rd, which tells you that there's more at this point. There's more. All we don't know if it's at equilibrium or not, but we know that there's more reactant than product. Okay, it's like 1. This is about 1 over 10,000. So there's about 1 product per 10,000 reactants. Okay, and then what we do is we plug everything in. We look up the delta G 0, and we come up with our values, and we find that okay, negative 44.9 kilojoules per mole, which says it's spontaneous under these conditions. All right. When delta G is equal to 0, Q is equal to K. Again, we have the relationships, and we can use those. All right. All right. So what we're going to do is look at this equation here. And this equation is the formation of silver chloride from its ions. So this is actually the reverse of the solubility of silver chloride. So what we do is just look up the KSP and take the reverse of it. So the K of this reaction is going to be 1 over the KSP. You just look up the KSP, and here's our K. All right, and then what we do is we got delta G equals minus R. Okay, here's temperature, and then you figure out etc. And you get delta G is equal to negative 56 kilojoules per mole, which tells us it's spontaneous and that this reaction would take place at this temperature. Which kind of makes sense because if you have silver and chloride in a solution, it usually precipitates out, which is kind of against what you might expect, because you're going from less ordered to more ordered. So let's think about that for a second here before we move on. So in this case, the entropy is actually decreasing. All right. So then that's not good. So why is the reaction going to take place? We know it's going to take place. So the reason it's going to take place is because the entropy must be good. So this must release heat. Okay. So this is exothermic reaction, and it counters the decrease in entropy. Okay, so if you have a system that's at equilibrium, again, it's both. The delta G products equal the reactants, and again, it's like water freezing, okay, at 32 degrees. And this should be arrow going back this way as well. And you can take a look at that. And let's move on here. Okay. All right, so when delta G is equal to 0, what we can do is find at what temperature the delta G is equal to 0. And what you can do is you can just rearrange the equation to find that. So if you know the delta H and the delta S, you can figure out the temperature where the system is going to be at equilibrium. Now, just to be clear, this is only possible for temperature-dependent reactions. And that's when the entropy and the enthalpy are opposite of each other. That means the enthalpy, and turns out the signs are the same. So if enthalpy is good, which means it has a negative term, and entropy is bad, which is a negative term, that is a temperature-dependent reaction. Okay, now what I would do if I wanted to find out, what I would do is if I was given that, so if delta H was negative and delta S was negative, okay, I find those two, I plug those two terms in, make sure they're all both in joules, and then solve for the temperature that is at equilibrium. Okay, because both terms are negative, below that temperature, the reaction will take place. Now, on the other case, if delta H is positive, which is not good, and delta S is positive, which is good, okay, that's a temperature-dependent situation as well. Okay, if I want to figure out what temperature they're at equilibrium, I go ahead and put those numbers in. And any temperature above that is where the reaction will take place. Okay, so here's an example how you have a chemical reaction. Beryllium liquid going to beryllium, bromine liquid going to bromine gas. Okay, I look at delta H liquid and delta S, and I come up that has a positive. Has the temperature at equilibrium is 334 Kelvin. Now let's take a look at these numbers here. Okay, this is a positive value, which means delta H is not good. This is a positive S, which means good. So this is definitely temperature dependent. And I should have said that all along, it's temperature dependent, not temperature independent. All right, so since both of these are positive, anything above, if we do above 334, this reaction will take place. Okay, and you can see that here. So temperature greater than 334, this reaction will take place. Below won't. And this is boiling, liquid going to gas. So this is the boiling point of this. So at 334, if you when you boil this, the liquid is turning into gas, and gas is turning into liquid. Okay, let's do this thing here. You go from solid to a liquid. That means you're melting. The delta H is positive. And these are the three values. Okay, we're just going to be using the H and the S. We're not going to be using this term here because we want to find out what temperature this reaction takes place. I mean, it's at equilibrium. This is a temperature dependent reaction because this is positive, which means it's endothermic, not good. This positive means it's increased enthalpy, which is entropy, which is good. We solve for temperature. And here's the equilibrium temperature, which is 256 Kelvin. All right, since both of these are positive above 256, the reaction will take place. Okay, typically what we do is we kind of assume that our values, even if we're not at 298, when we plug these values in from the tables, they're still going to be pretty close to what we expect. Okay. All right. So this reaction says I want to figure out the calculate delta G for this here. So what you can do is you can look up on your tables, and then you can figure out the delta H and the delta S using the product minus the reactants. And when you do that, you end up with these two here. And let's just take a look at them. So this is good. So this is this exothermic reaction, but the entropy is not good. So this is a temperature dependent reaction, negative. So what we can do is we can figure out the temperature where this is. Okay, so that is at equilibrium, and then any temperature below that, the reaction will take place. Okay. So we go ahead and plug it in. What we do is we want to figure out first of all figure out delta G. So we figure out delta G, and we're not going to figure out the equilibrium temperature here. So we'll just figure out delta G at 298 or 25 degrees C. So we just plug it in, and we get that the reaction does take place at 298. Okay. All right, now what we can do is change the temperature and plug everything in. Now, even though we're not at 298, we can use the same values as we did before and plug it in, and we find that this reaction is not spontaneous at 61. I mean at 773 Kelvin. Okay. All right. And also what I would like to do, and I'm not going to do it here, I'm sure, is I solve for the equilibrium temperature and find out what temperature this reaction is spontaneous or non-spontaneous. All right. Next thing I'm going to do is I'm going to figure out the equilibrium constant of this reaction. I know the delta G is negative 33.3. Okay, so now I can just plug I have the equilibrium expression in terms of delta G. I plug that in, I get K is equal to 10 times 10 to the minus fifth, which says that there's a whole lot of product formed per reactant. which definitely tells me it's definitely spontaneous. More product than reactant. And that jives with what we talked about here. Delta G is negative. That means spontaneous, and more product than reactant, spontaneous as well. And there you go. Go ahead and figure this one out. Okay, so you can see in this case, delta G is negative 234, and we plug it in, we can see it's really, 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 really spontaneous. Okay, there's a lot of product form for reactant. When you look at this, you would hardly notice any reactant left over at all. Okay, and this is the final slide, and this shows you just all the equations that you will be using for all of these. Okay, so that ends this lecture, and I'll be sending some problems out for it over the next couple of days and make them due probably by the end of the week as well. You guys are doing well, doing good with all this, and hopefully you're learning something. Okay, talk. If I don't talk to you later, maybe I'll see you sometime. All right, I'll send out a notice soon about I need to download this. It's gonna take me a while, and so I'll get it out by tomorrow. Okay.